and welcome to MATLAB programming for numerical computations. We are now in week 4 of this course. In this week we are going to cover linear equations. So, basically we are going to cover linear algebra in the first lecture, lecture 4.1, followed by several methods to use linear algebra to solve the problems of the nature Ax equal to b to find the values of the vector x. Before we do that, let us recap some of the results from linear algebra. For this, the related videos are in the computational techniques course, module 3 lecture 1, the link for which is given in front of you. So, let us review some of the results in linear algebra. So, what is a vector? Vector is nothing but an ordered set of scalars. An example is shown over here. So, this vector has a dimension. In this case, the dimension of this vector is 2. As convenience, what we are going to do in this entire lecture series, we are going to assume all the vectors to be column vectors, which means that the vectors will have n rows, but a single column. As you can see over here, we have 2 rows, but a single column. Now, this column vector has a dimension which is nothing but the number of elements. If we want to look at the geometric interpretation, this could be nothing but a point in the space, in a 2-dimensional space, which is the distance 2 on the x axis and a distance 3 on the y axis, or more appropriately distance 2 on the first axis and distance 3 on the second axis. Now, this particular vector has a direction which is basically given by the value 2, 3, as well as it has a norm. Now, the most common norm that we are used to so far is what is known as this 2 norm of this vector, which is nothing but the square of the distance of that particular point from origin. So, square root of 2 square plus 3 squared is nothing but the 2 norm of this particular vector. Likewise, we have the 1 norm of the vector, n norm of the vector, or infinity norm of the vector, something we are not going to go into, but essentially just the way we associate distance with a physical point in space, a vector can be associated with a norm which is nothing but an indication of the size or the distance of that particular vector. Okay. Now, next case we have seen is what does it mean when we want to solve 2 equations in 2 unknowns. So, here I am showing 3 different cases of 2 equations and 2 unknowns. The unknowns are x1 and x2, and the 2 equations can actually have a single solution, can have 0 solution, and can have infinite number of solution. So, when do we get a single solution, 0 solution, and infinite number of solution? We are showing graphically on this slide. Okay. So, if you look at the first example, we have the equation x1 plus 2x2 equal to 1, x1 minus x2 equal to 4. These represent the blue and the red line over here, and these 2 lines intersect at a point 3 minus 1. So, 3 minus 1 is a unique solution. Okay. Next is, if these 2 equations, instead of having x1 minus x2 as the second equation, if we were to have 2x1 plus 4x2, which is nothing but the double of the left hand side as the left hand side of the next equation, which is 2x1 plus 4x2, that is the left hand side of the next equation, and the right hand side, if we take that value as 4, we can see that these now represent 2 parallel lines. These 2 parallel lines are not going to intersect, and we are going to have 0 solutions in this case. And now, in this case, if the second equation was nothing but double of the first equation, so 2x1 plus 4 times x2 equal to 2, which is nothing but double of this first equation, we are going to have these 2 lines lying on top of each other, and we are going to have infinite number of solutions. So, the question is, when do we get single solution, when do we get infinite number of solution, and when do we get 0 solution? Okay. And answer to that is from finding out the rank of the matrix. So, if we look at the rank of matrix A, and if the rank of matrix in this particular case was equal to 2, we are going to have a unique solution. If rank of a square matrix of an n by n dimensional square matrix is equal to n, then we will have a unique solution for the problem Ax equal to b. Okay. But what if the rank is not equal to 2? That is the case that we see in the middle column as well as to the right column. In that case, we need to look at the rank of the matrix A comma b. If rank of matrix A comma b is equal to the rank of A, then we are going to have infinite number of solutions. But if rank of A comma b is not going to be equal to rank of A, then we are going to have 0 solutions. Okay. Let us go on over to MATLAB and look at these 3 examples that we have seen. So, let us look at the matrix A. Matrix A is 1, 2, 1, minus 1. B is the right hand side, that is 1, 4. Okay. So, these are the 2 the values that we have when we want to solve Ax equal to b. We know that the solution x is going to be I and v inverse of A multiplied by b, okay, and x, as you can see over here, is 3 comma minus 1, something that we had seen in our PowerPoint slide a minute earlier. Okay. Now, MATLAB has a more efficient way of solving these equations, and that is using slash, in this case backslash, because we are pre-multiplying inverse of A with b. So, we write this as A backslash b, and when we press enter, we are going to get the solution 3 comma minus 1. A backslash b for an A which has a rank equal to n is exactly same as this particular command. Okay. Let us do help slash and see what we get. Okay. If you recall what we did in the first module, we had looked at element by element division and element by element operations, and this is what the latter part of this help slash showed us. But what we are more interested in is to look at what the left division and right division actually mean. So, A backslash b is left division, which is same as INVA multiplied by b if A is an n by n matrix with rank equal to n. Okay. It is something different if the rank of A is not equal to n, we will not go into that right now. And then we have an equivalent called a right division. Right division is b multiplied by inverse of A. Okay. For the problem Ax equal to b, we needed to have a left inverse. So, x was inverse of A multiplied by b, not b multiplied by inverse of A, and therefore, we had a left inverse which is indicated by a backslash, A backslash small b over here, not capital B, and that is what the solution that we got. Okay. So, that was the first thing that we saw, how to solve these equations. Let us look at how to find out using MATLAB whether or not your equations are going to have a unique solution or infinite number of solutions or 0 solutions, and we can do that by using the command rank A, and rank of matrix A is equal to 2. So, A we say is a full rank matrix. That means A, the rank of A is equal to the number of rows or the number of columns of matrix A. Okay. We can also find the size of matrix A by saying m comma n equal to size A. M is going to be number of rows, n is going to be number of columns. We have already seen that in module 1. Let us now look at the second example, and the second example our B remained the same. We changed our A to 1 to 2 4. Let us make that change, A equal to 1 2 2 4. Let me echo this by skipping the semicolon. Okay. So, our A is 1 2 2 4. Let us get rank of A, and rank of A equal to 1. Okay. And therefore, A will not have a unique solution. Ax equal to b will not have a unique solution. It can either have infinite number of solutions or 0 solutions, and to do that we need to find the rank of matrix A comma b. and the rank of matrix A comma B equal to 2, which means that the rank of A comma B is not the same as rank of A. So, we are going to have 0 solutions, that is this particular case. Now, let us change B to 1 2, B equal to 1 semicolon 2. Note that we have used a semicolon because we want a column vector. So, that is our B. Rank of A is not going to change because we have not changed rank, we have not changed the matrix A. Let us now look at rank of A comma B, and rank of A comma B in this case equals rank of A, in which case you are going to have infinite number of solutions. Okay. Let us now look at the next concept in linear algebra, and that concept is what is known as condition number. In these two examples, we had equation x1 plus 2x2 equal to 1 and x1 plus 4x2 equal to 2. Instead of the second equation being x1 plus 4x2, if we were to change this to 3.999x2, okay, we are going to get this particular equation, okay, and our matrix A is going to be 1 2 2 3.999. If we solve this equation, we are going to get the solution as 3 comma minus 1. Now, if we make a very small change in our B, that means instead of 1 and 2.001, if we change it to 1 and 2.0, we are going to have a very large change in the solution. And the reason for this is what is known as condition number, or what is known as a poorly conditioned matrix. Condition number is nothing but the ratio of eigenvalues of the matrix. So, in this particular case, A being an n by n matrix has 2 eigenvalues, and the ratio of 2 eigenvalues in this case is approximately 25,000, which is a fairly large number, and therefore, we see that the results change quite significantly for a reasonably small change in B matrix. Okay. So, let us look at the condition number of A when A was defined as 1 2 to 3.999, that was our A matrix. We will use the command COND in order to find the condition number of A, and COND A is 2.5, was approximately 2.5 into 10 to the power 4, which is approximately 25,000. Now, we can find eigenvalues of A using the command EIG, and EIG will give you 2 eigenvalues, and we can also verify that the condition number is the ratio of the 2 eigenvalues, okay, and the absolute value of that. Yeah, and this is exactly what our condition number is that we obtained using the command COND. So, the MATLAB command COND is for finding condition number of any matrix. The MATLAB command rank is to find out the rank of that particular matrix, and the MATLAB command EIG is the command for finding eigenvalues of that matrix. Now, let us go back and look at what else our eigenvalues command can do. So, I will type help EIG, okay, and so we can see that eigenvalues. So, if we give a command EIG with just one output argument, we are going to get a column vector containing eigenvalues. However, if we give 2 arguments V and D, V is going to be a matrix containing the eigenvectors, and D is going to be the matrix whose diagonal elements are the eigenvalues. So, let us look at that in MATLAB. V comma D equal to EIG. Okay. So, as remember just a few minutes back we had said that we will define vectors as column vectors. So, this is the eigenvector 1, which is minus 0.89 0.45, that is the first eigenvector corresponding to this eigenvalue. The second eigenvector is this guy, which corresponds to this eigenvalue. Okay. Let us look at whether this satisfies the equation, rather A multiplied by V equal to lambda multiplied by v, whether this is satisfied or not. Okay. Let us try to look at that. Okay. So, let us say L was nothing but d1, okay, and our v was nothing but the first column. The first column basically means all the rows and column number 1. This L is the first eigenvalue, this v is the first eigenvector. Let us say A multiplied by v minus lambda multiplied by v. What we get is, we get the value as 10 to the power minus 15. Let us look at the value of A multiplied by v, and A multiplied by v is of the order of 10 to the power minus 3. So, for all practical purposes, this particular guy A multiplied by lambda is almost equal to lambda multiplied by v. Okay. Again, keep in mind what we had said earlier in the previous 2 modules is computer is a finite precision machine. What that means is that computer has a least count. So, when we are going to do problems using floating point numbers, using real numbers, we are not always going to get, when we do A minus B, we are not always going to get the value equal to 0 if A and B are equal. We are going to get sometimes value of A minus B as a very small number compared to value of both A and B. And that is what essentially we are looking for, is whether or not A multiplied by V is close enough to lambda multiplied by V. So, A multiplied by V is this value and lambda multiplied by V is also the same value. Let us look at the other example where we take the lambda as the second eigenvalue. So, L is d2 comma 2 and V is nothing but V all the rows and second columns. Okay. Let us look at A multiplied by V. This is the value of A multiplied by V, and let us look at lambda multiplied by V, and that is the same value that we get as lambda multiplied by V. Okay. So, to recap what we did use the command EIG to find eigenvalues and eigenvectors. When you run the command with 2 arguments, the first argument will give you a matrix containing the eigenvectors. The first column of that matrix is the first eigenvector, second column of that matrix is second eigenvector, and so on. The second argument from EIG is a matrix whose diagonal elements are the various eigenvalues. The first A11 is the first eigenvalue, A22 is the second eigenvalue, and so on. ANN is the nth eigenvalue. So, that is the review of the linear algebra that is going to be useful for rest of this course, and let us now recap all the useful MATLAB functions that we have done so far. In the previous lectures, in module 1 primarily, we have looked at matrix exponent, matrix logarithm, matrix square root, matrix power, and today we also looked at matrix division, left division as well as right division. So, these were the commands that we have covered before in modules before. Today we covered the command INV to find inverse of a matrix, rank to find rank of a matrix, COND to find condition number of matrix. We will also in a minute use the command norm to find norm of a vector or a matrix. We will just stick ourselves to vectors for now, but a norm exists for a matrix as well. Okay. We also used EIG to find eigenvalues and eigenvectors, LU, Cholesky, QR factorization, SVD, Schur decomposition. These are something that a lot of engineers use quite a bit, and I have put them in this particular table just for the sake of completeness. LU decomposition is something that we are going to cover in the 4th lecture of this module. Okay. However, you do not have to worry about the remaining things, singular value decomposition or Schur decomposition or Cholesky factorization and so on, for the purpose of this course. Okay. Okay. So, let us finally now let us go and find out the norm. So, let us look at our vector x. Now, norm of this vector is nothing but 3 squared plus 1 squared square root of that, which is square root of 10. So, norm of x is going to be square root of 10, which is nothing but 3.1623. Okay. So, norm is an indicator of the size of any vector. So, with that we come to end of lecture 1 of module 4. So, what we have done in lecture 1 of this particular module is to cover the basics of linear algebra. So, primarily we have looked at trying to solve equations of the form Ax equal to b, looked at eigenvalues and eigenvectors of A, what does the condition number mean, what does rank mean, and how we can use rank in order to find out whether we will get unique solutions, infinite number of solutions or 0 solutions to an equation of the form Ax equal to b. So, that ends this lecture for recapping linear algebra, and see you in the next lecture. Thank you.